Chapter 8, Cleaning. Introduction. We begin our study of the most critical function within the sterile processing department, the decontamination process. The primary function of the decontamination area is to receive soiled medical devices and render them safe for handling and further processing. This process relies strictly on cleaning. In this context, cleaning is defined as the removal of contamination from an item to the extent necessary for further processing or for its intended use. Cleaning involves the physical removal of organic and inorganic soils. Organic soils include biological matter such as blood, protein, and bone. Inorganic soils include dust, rust, and mineral deposits. To achieve this, technicians typically use water combined with detergents or enzymatic products. It is vital to understand the distinction between cleaning and sterilization. Sterilization kills microorganisms, whereas cleaning removes the soil that protects them. The motto of the sterile processing department is, "You can clean without sterilizing, but you cannot sterilize without cleaning." This is not just a saying, it is a scientific fact. If soil, such as dried blood or bone, remains on an instrument, it acts as a shield. This shield protects microorganisms from the sterilizing agent, whether the agent is steam, chemical, or radiation. Even the most advanced sterilizer cannot penetrate thick layers of dried biological matter. Therefore, a dirty instrument that goes through a sterilization cycle is still a non-sterile, dangerous instrument. What is clean? In the context of sterile processing, the definition of the word clean is specific and technical. First, we look at visual cleanliness. In general terms, clean refers to the absence of visible soil. However, in medical device processing, visual inspection is just the first standard. We must adhere to the clinical definition. According to industry standards established by AAMI and HSPA, cleaning is defined as the removal of all visible and non-visible soil and other foreign material from the medical device being processed. We must also distinguish between the terms clean and sterile. When an item is classified as clean, it means the item is free of soil and has a reduced bioburden, but viable microorganisms may still be present. When an item is classified as sterile, it means the item is completely free of all living microorganisms, including bacterial spores. To achieve a clean state, the technician must master a combination of 4 elements, known by the acronym TACT. 1. Time. This refers to the duration of soaking or the cycle time of a machine. 2. Action. This refers to the mechanical scrubbing friction or the ultrasonic cavitation used to dislodge soil. 3. Chemistry. This refers to the specific detergents and enzymes selected to break down the soil. 4. Temperature. This refers to maintaining the correct heat levels required for the chemicals and equipment to function effectively. Introduction to the decontamination area. The decontamination area is the dedicated physical space within the sterile processing department where soiled medical devices are received, sorted, cleaned, and disinfected. Because this room houses contaminated items, it is a restricted area designed to contain biohazards and prevent the spread of pathogens to the rest of the facility. Design and location. To maintain this containment, the physical design of the decontamination area is driven by the principle of one-way flow. The workflow must always move from dirty to clean, never the reverse. Ideally, the decontamination area is located on the same floor as the operating room to facilitate the quick transport of soiled items. If the area is located on a different floor, dedicated dumbwaiters or elevators must be used to transport soiled case carts. There must be a physical barrier separating the decontamination area, which is the dirty side, from the preparation and packaging area, which is the clean side. This barrier can be a wall with a pass-through window or a door. This physical separation is mandatory to ensure that aerosols generated during cleaning do not cross-contaminate the clean instruments on the other side. Furthermore, the floors and walls must be constructed of non-porous, water-resistant materials that can withstand frequent cleaning with harsh chemicals. Carpet is strictly prohibited in this area. Engineering controls. Beyond the physical walls, we rely on engineering controls. These are mechanical systems built into the facility to minimize the risk of exposure to biohazards. The first critical control is negative air pressure. The decontamination area must be maintained under negative air pressure relative to adjacent areas. This means that when a door is opened, air flows into the decontamination room from the clean hallway. This air current acts like an invisible barrier, keeping airborne contaminants and aerosols trapped inside the decontamination room so they cannot escape into the hospital corridors. The ventilation system must provide a minimum of 10 air exchanges per hour. This constant cycling of air serves to dilute and remove airborne pathogens. Crucially, the exhaust air from this room must be vented directly to the outside atmosphere. It must never be recirculated into the hospital's general HVAC system. Regarding the environment, the temperature in the decontamination area should be controlled between 60 degrees Fahrenheit and 65 degrees Fahrenheit, 60 to 65 degrees Fahrenheit, or 16 to 18 degrees Celsius, 16 to 18 degrees Celsius. This lower temperature range serves two vital purposes. First, it inhibits the growth of microorganisms, which tend to thrive in warmer temperatures. Second, it provides comfort for technicians who must wear heavy, heat-retaining personal protective equipment, PPE. Alongside temperature, the relative humidity should be maintained between 30% and 60%. Safety infrastructure is also part of engineering controls. Dedicated hand-washing sinks must be located near the entrance and exit of the decontamination area to encourage frequent hand hygiene. These sinks must be separate from the sinks used for cleaning instruments. Additionally, per OSHA requirements, an emergency eye wash station must be accessible within 10 seconds of potential chemical exposure sites. This equates to a distance of approximately 55 feet. Traffic control and environmental management. Because the decontamination area is a designated biohazard zone, strict traffic control measures must be enforced. Access is restricted to authorized sterile processing personnel only. Visitors, vendors, and unauthorized hospital staff are strictly prohibited from entering unless they are wearing appropriate personal protective equipment and have received safety training. The dress code is rigid. Everyone entering the decontamination area must change into facility-issued scrub attire. Street clothes are not permitted. Upon entry, full PPE, including a gown, gloves, mask, face shield, and shoe covers, must be donned immediately. Workflow discipline is equally important. Personnel should never move from the decontamination area directly to the clean assembly area without first removing all PPE and washing their hands. The principle of one-way flow applies to people as strictly as it applies to instruments. Finally, we address housekeeping. The environment itself must be cleaned daily. Floors should be wet mopped using a hospital-grade disinfectant. Work surfaces, sinks, and frequently touched objects such as door handles and phones should be cleaned at the beginning and end of each shift. This routine is essential to reduce the environmental bioburden. Work area setup. Within this carefully controlled environment, the physical setup of the manual cleaning station is critical for both workflow and ergonomics. The industry standard for manual cleaning is known as the 3-sink arrangement. This method dictates a specific sequence of events across 3 separate basins. Sink 1 is the wash sink. This sink contains fresh water mixed with the appropriate detergent, which is usually an enzymatic product. It is used for the mechanical removal of soil. The water temperature in this sink must be monitored closely to ensure it falls within the range specified by the detergent manufacturer. This is often between 109 degrees Fahrenheit and 140 degrees Fahrenheit, because enzymes are biological proteins that die and become ineffective at higher temperatures. Sink 2 is the intermediate rinse sink. This sink contains plain tap water. Its sole purpose is to rinse off the dissolved soil and detergent residues loosened during the first step. The water in this sink must be changed frequently. If it is not changed, it becomes dirty water that recontaminates the instruments instead of rinsing them. Sink 3 is the final rinse sink. This sink must contain critical water, such as deionized, reverse osmosis, or distilled water. This water has been treated to remove minerals and impurities. Using critical water for the final rinse is mandatory to prevent water spots, staining, and instrument corrosion. Furthermore, it helps remove pyrogens, which are fever-producing substances often caused by dead bacteria found in tap water. In addition to the sinks, we must consider ergonomics. Workstations and sinks should ideally be height adjustable to accommodate technicians of different statures. This prevents severe back strain during long periods of scrubbing. Regarding lighting, adequate illumination is essential for visual inspection. Lighted magnification lenses should be available at the sink to help technicians identify small debris hidden in crevices. Cleaning tools. The effectiveness of this manual cleaning process depends entirely on using the correct tool for the specific instrument. Using the wrong tool can damage the passivation layer of the instrument, leading to corrosion and harbored bacteria. Brushes are the primary tool for cleaning lumens, which are tubes and textured surfaces. First, we have nylon bristle brushes. These are the standard for general cleaning. They are stiff enough to remove soil but soft enough that they will not scratch stainless steel. Second, we have brass bristle brushes. These are used only on specific, durable surfaces like tungsten carbide inserts, which are found on gold-handled needle holders, or for removing stubborn bone cement. They should never be used on standard stainless steel as they will scratch the surface. Third, we have stainless steel or metal brushes. These are generally prohibited for use on surgical instruments. They are too abrasive and will cause severe damage and micro scratches, creating hiding places for bacteria. Sizing is also critical. When cleaning a lumen, such as a suction tip, the brush must be the exact diameter and length of the lumen. A brush that is too small will miss soil, while a brush that is too large can get stuck or damage the internal lining. Beyond brushes, technicians use sponges and cloths. These must be soft and lint-free. If lint or fibers are left on an instrument, they can enter a patient's body during surgery. The body will attack these fibers, causing a foreign body reaction known as a granuloma, or potentially causing an embolism. Finally, we use water spray guns. These are pressurized water nozzles used to flush lumens. When using these, technicians must be careful to ensure the spray does not generate excessive aerosols, which could spread contaminants through the air. Mechanical cleaners. While manual cleaning is essential for delicate or complex items, mechanical cleaners provide consistency and efficiency that human hands cannot match. The two most common mechanical units are ultrasonic cleaners and washer disinfectors. Ultrasonic cleaners, often called sonics, are automated devices used to remove fine soil from crevices, box locks, and serrations that manual brushing simply cannot reach. The principle of operation for these machines is called cavitation. The machine uses high-frequency sound waves to create microscopic bubbles in the solution. These bubbles grow until they become unstable and implode, meaning they burst inward. This implosion creates a vacuum effect that physically pulls soil away from the instrument surface. There are key operational guidelines for using ultrasonic cleaners. First, degassing. Before use, fresh water must be degassed, which means running the machine empty for a cycle. This removes excess air bubbles that would otherwise cushion the cavitation effect and reduce cleaning efficiency. Second, the lid must always be closed while the machine is running to prevent the aerosolization of biohazards generated by the bubbling action. Third, material compatibility. Not all materials are safe for ultrasonic cleaning. Chrome-plated instruments that are peeling, ebonized or black instruments, and rigid endoscopes or cameras are often damaged by the intense vibrations. Finally, placement is critical. Instruments must be placed in a wire mesh basket, never stacked, and box locks must be open to allow the solution to reach all surfaces. Washer disinfectors. The automated washer disinfector is the workhorse of the decontamination area. Unlike ultrasonic cleaners, which use vibration, washer disinfectors use impingement. Impingement is the spray force action of pressurized water against instruments to physically remove bioburden. A standard cleaning cycle in a washer disinfector typically consists of several distinct phases. Phase 1 is the pre-rinse. This cycle uses cool water to wet the instruments and rinse off gross soil. It is critical that cool water is used. If hot water were used in this first step, it would coagulate, or cook, the protein in blood onto the metal, making it nearly impossible to remove. Phase 2 is the enzymatic Washington detergent is introduced, and the water is heated to a temperature optimized for the enzyme, usually between 100 degrees and 140 degrees Fahrenheit. Phase 3 is the Washington. This is a higher temperature wash, often between 140 and 180 degrees Fahrenheit, using detergent to break down remaining soil. Phase 4 is the rinse. This involves thorough rinsing to remove all chemical residues. Phase 5 is thermal disinfection. This is the most critical step for staff safety. The machine raises the water temperature, typically to between 180 degrees Fahrenheit and 203 degrees Fahrenheit, 180 to 203 degrees Fahrenheit, or 82 to 95 degrees Celsius, 82 to 95 degrees Celsius. It holds this temperature for a specific contact time, such as 1 minute at 194 degrees Fahrenheit. This step kills most vegetative microorganisms, rendering the instruments safe to handle with bare hands on the clean side. Note well, this is disinfection, not sterilization. Phase 6 is lubrication. Some machines apply a water-soluble instrument lubricant, often called instrument milk, during the final rinse. Phase 7 is drying. Hot air is blown to dry the instruments. To ensure these machines work, technicians must follow loading guidelines. Hinged instruments like scissors and hemostats must be fully opened or unratcheted so water can reach the box lock mechanism. Trays should not be overloaded or stacked. Complex instruments must be disassembled. Finally, items with concave surfaces, like kidney basins or bowls, must be placed upside down or on an angle so water drains off and does not pool. Automated cart washers. Beyond the specialized cleaning of surgical instruments, we must also address the transport equipment. Automated cart washers are large mechanical units designed primarily to clean and sanitize the metal case carts used to transport surgical trays. They operate similarly to a commercial car wash. Their function is to remove the heavy contamination picked up by case carts during transport through hospital corridors and elevators. In addition to carts, these machines are often used for rigid sterilization containers, which are the blue metal bins, as well as surgical basins and bowls. However, it is vital to note that cart washers are generally not used for delicate surgical instruments. This is due to the high water pressure and the lack of precise racking, which could cause instruments to bounce around and sustain damage. The cycle typically involves a high-temperature wash and thermal disinfection. The carts exit the machine hot and dry. Most units are floor-loaded, allowing technicians to roll heavy carts directly inside without lifting, which is an important ergonomic feature. Equipment testing. Having these machines is not enough. We must verify they are working. Just because a machine runs a cycle does not mean it cleaned effectively. Machines can fail due to clogged spray arms, insufficient water pressure, or heating element failures. Therefore, cleaning verification is mandatory to ensure equipment performance. First, we look at testing ultrasonic cleaners. The efficiency of the ultrasonic waves, specifically the cavitation process, must be tested daily. There are two primary methods. The first is the use of commercial tests. These are typically glass vials containing a reactive solution that changes color when exposed to effective cavitation energy. This is the industry standard method. The second is the traditional foil test. This involves placing a sheet of aluminum foil in the tank and running a short cycle. Upon inspection, the foil should show uniform pitting, which looks like tiny pinholes, across the entire surface. If there are smooth areas on the foil, it indicates blind spots in the tank where cavitation is not happening, meaning instruments placed there will not be cleaned. Second, we look at testing washer disinfectors. The industry standard challenge device for these machines is called the TOSI, or Test Object Surgical Instrument. This device mimics a surgical instrument with dried blood, specifically a protein-based soil, hidden in a crevice. The procedure is straightforward. The TOSI is placed in the washer cart, usually on the bottom shelf or in a difficult-to-reach area. After the cycle is complete, the device is inspected. If any red residue remains inside the gap, the cycle is considered a failure. Regarding frequency, this testing should be performed daily, usually on the first load of the day, and after any major repairs to the equipment. Instructions for use. Before we can apply any of these chemicals or methods, we must consult the ultimate authority in the decontamination room, the Instructions for Use, or IFU. The IFU is a document provided by the device manufacturer that provides detailed, step-by-step instructions on how to properly clean, disinfect, sterilize, and handle a specific medical device. The golden rule of sterile processing is simple: always follow the manufacturer's instructions for use. It is crucial to understand the legal authority of this document. The IFU is not merely a suggestion or a helpful tip, it is a validation document reviewed and cleared by the FDA. If a technician deviates from the IFU, for example, by using a different chemical, skipping a cleaning step, or using the wrong sterilization cycle, and a patient is subsequently injured, the facility is liable for negligence. You are legally required to follow these written instructions. A common dilemma in the field occurs when the chemical manufacturer's label disagrees with the instrument manufacturer's IFU. For instance, a detergent label might claim it is safe for all metals, but the specific IFU for a rigid endoscope might say, "Do not use detergents with a pH above 7.5. In such conflicts, the rule is clear: generally, the instrument manufacturer's IFU takes precedence regarding material compatibility. They know exactly what their device is made of and what will damage it. Finally, accessibility is key. These instructions must be readily accessible to all staff in the decontamination area. Whether they are stored in physical binders or digital databases, technicians must be able to consult the document immediately whenever they process an unfamiliar item. Guessing is never an option. Steps in the decontamination process. With our tools, chemicals, and regulations in place, we now look at the workflow itself. While specific steps vary by device according to the IFU, the general workflow in the decontamination area follows a logical sequence designed to minimize risk and maximize cleaning efficiency. Step 1 is point-of-use treatment. This actually occurs in the operating room. The item arrives at the decontamination area already moist and with gross soil removed. Step 2 is soiled receiving and sorting. Upon arrival, items are sorted by their cleaning requirements. This is a critical safety step. Delicate items, such as cameras and scopes, must be separated to prevent damage from heavier instruments. Non-immersible items, such as powered drills and batteries, must be separated immediately so they are not accidentally dropped into water, which would destroy them. Sharps must also be identified to prevent injury. During this sorting phase, disassembly must occur. Any multi-part instrument that was not disassembled in the operating room must be taken apart now. If a device is cleaned while assembled, soil will remain trapped between the mating surfaces. No sterilant can penetrate that trapped soil later in the process. Step 3 is cleaning, which involves both manual and mechanical processes. Instruments with dried soil may need to soak in an enzymatic solution to loosen debris. Manual cleaning involves brushing lumens and scrubbing crevices under the surface of the water to prevent aerosolization. Following manual cleaning, suitable items are loaded into ultrasonic cleaners or washer disinfectors. Step 4 is inspection. After cleaning, items must be visually inspected for remaining soil before they leave the decontamination side. This is non-negotiable. If visual soil is found, the item must be returned to the beginning of the cleaning process. You cannot simply wipe it off, the entire cleaning cycle must be repeated. Step 5 is quality testing or cleaning verification. This involves periodic testing to verify that the cleaning equipment and manual processes are working effectively. This may include the TOSI test we discussed or adenosine triphosphate, or ATP, detection to check for invisible organic residue. The final step is decontamination or disinfection. This typically involves the final thermal disinfection cycle in the washer disinfector. This microbicidal process renders the item safe for handling. Once the cycle is complete and the item is dry, it is passed to the clean side, known as the preparation and packaging area. Cleaning chemicals and lubricants. To successfully execute the decontamination workflow we just described, we must return to the chemistry element of the tact circle. Using the wrong chemical can ruin expensive instruments or, worse, fail to remove soil. First, we examine enzymatic products. Enzymes are biological catalysts, which are proteins that speed up chemical reactions. In sterile processing, they act like Pac-Man, eating specific types of soil. It is vital to match the enzyme to the soil. There are 3 main types. First is protease. This enzyme breaks down proteins, such as blood, mucus, feces, and albumin. Since most surgical soil is blood-based, protease is the most important enzyme for our field. Second is lipase. This enzyme breaks down fats, such as bone marrow and adipose tissue. Third is amylase. This enzyme breaks down starches and carbohydrates. Because enzymes are living proteins, they are highly sensitive to temperature. If the water is too cold, they remain dormant and do not work. If the water is too hot, usually above 140 degrees Fahrenheit or 60 degrees Celsius, they die, or denature, and stop working. The optimal range is typically 100 degrees to 140 degrees Fahrenheit. Next, we look at detergents. Detergents work by lowering surface tension and suspending soil in the water, a process called emulsification. For mechanical washers and ultrasonic cleaners, it is mandatory to use low-foaming detergents. If a detergent creates high foam, it will block the spray action of washer arms and interfere with ultrasonic cavitation, rendering the machine useless. We must also consider pH levels. Neutral pH detergents, ranging from 7.0 to 8.0, are the safest for most instruments, including aluminum and plastic. This is the most common choice in the department. Alkaline detergents, which have a high pH, are more effective at removing heavy organic soil but can corrode aluminum containers or rigid scopes if not thoroughly neutralized. Acidic detergents, which have a low pH, are rarely used for general cleaning but are primarily used to remove mineral deposits or rust. Finally, we address lubricants, often referred to as instrument milk. Stiff joints on hinged instruments like scissors and needle holders can cause surgeon fatigue and lead to instrument breakage. To prevent this, lubricant is applied after cleaning and before sterilization. The most critical rule is that surgical lubricants must be water-soluble. This allows steam to penetrate through the lubricant film during sterilization. Technicians must never use oil, grease, or WD-40. These substances are not water-soluble. If applied, they create a barrier that prevents the sterilizing agent from reaching the instrument surface, resulting in a non-sterile, dangerous instrument. Conclusion. We have now covered the extensive details of the cleaning process. It is important to step back and remember why this matters. Cleaning is the single most important step in the reprocessing of medical devices. It is the absolute prerequisite for sterilization. If an instrument is not thoroughly cleaned, the sterilization process, whether it is steam, chemical, or plasma, is guaranteed to fail. The presence of soil creates a physical barrier that prevents the sterilizing agent from contacting the surface of the instrument. This leaves viable pathogens protected underneath, ready to infect the next patient. The sterile processing technician must master the science of tact, which stands for time, action, chemistry, and temperature, and must strictly adhere to the manufacturer's instructions for use. From the manual brushing of complex lumens to the validation of automated washer disinfectors, every action in the decontamination area is a critical defense against healthcare-associated infections. Sterile processing terms. To conclude this chapter, we will review the key technical terms you must know for your exam. Aerosol. This is a suspension of ultramicroscopic solid or liquid particles in the air. In our department, aerosols containing pathogens can be created dangerously during manual scrubbing or ultrasonic cleaning if lids are not used. Cavitation. This is the process used in an ultrasonic cleaner where low-pressure bubbles in a cleaning solution burst inward, or implode, to dislodge soil from instruments. Deionization. This is a water treatment process where ions with an electrical charge are removed from the water. Detergent. This is a cleaning agent that lowers surface tension to dislodge soil and keep it suspended in the solution so it can be rinsed away. Emulsification. This is the process of binding two or more immiscible liquids, like oil and water, together. Detergents emulsify fats and oils to allow them to be washed away. Impingement. This is the spray force action of pressurized water against instruments to physically remove bioburden. This is the mechanism used in washer disinfectors. Pyrogen. This is a fever-producing substance. It is typically dead bacterial cells or their byproducts, such as endotoxins, that remain on instruments or in water supplies. It is important to note that an instrument can be sterile, meaning it has no living bacteria, but still have pyrogens, which can cause a patient to spike a dangerous fever. Reverse osmosis. This is a water purification process that uses a semi-permeable membrane to remove dissolved solids and impurities. Finally, we must distinguish between validation and verification. Validation is a documented procedure to establish that a process will consistently yield a product complying with predetermined specifications. This is the manufacturer's responsibility. They validate that their instructions work. Verification is a documented procedure used by the healthcare facility to confirm that the validated process is being delivered. This is the user's, or your, responsibility. You verify that you followed the instructions. This concludes our study of Chapter 8.